So hello everyone, welcome back to another lecture, another conformers lecture. In our previous lecture, we are talking about that what is conformers, difference between conformational isomers and configurational isomers. Then we are talking about the different kind of strain present in the conformers, and then we are talking about the naming of the conformer. So we are today we are beginning with acyclic conformers, but before that we are just recapitulate that what we have learned in the naming of conformers. Okay. So I hope that it must be remember about that particular thing that if your conformers a torsion angle between minus 30 degree to plus 30 degree, then the conformer is called as syn-periplanar. Similarly, plus 30 to plus 90 is called synclinar in clockwise direction, whereas in the minus 30 degree to minus 90 degree, that is the anti-clockwise direction rotation, is called minus synclinar. Similarly, 90 to 150 it's called anticlinal, and minus 150 to plus 150 it's called anti-periplanar. Now how to determine the naming? Okay, so basically what happened that in uh, in the conformers, basically there is a two carbon center present here. Now in this carbon center, the highest priority group and in the adjacent carbon center contains the highest priority group positions, relative position will determine the naming of the conformer. Like example here in this Newman projection formula, this particular carbon center that is present here, this particular carbon center having this particular Cl has the highest priority over these two hydrogen. Similarly, in the back carbon, which is this, here also Cl present in the highest priority order in terms of the rest two hydrogens. So to name this particular conformer, we have to check the relative position between these two Cl group. Okay, now here the two Cl group are anti-position. That means 180 degree torsion angle present between these two particular Cl compound. That means this particular compound name is anti-periplanar. And since it is completely 180 degree, so we can't use any positive or negative value here. Okay. Similarly, here also you can find that this particular Cl and this particular Cl is the nothing but a 120 degree apart. Now in our chart 90 to 150 degree range, it's called anticlinal. So similarly, it is present here, it is 120 degree, so it is called anticlinal. Similarly, here also you can find that the torsion angle between two chlorine molecules is 60 degree. 60 degree is lying in the range between 30 to 90 degrees, so this particular compound name is synclinal. Similarly, here these two are 0 degree apart. Okay, so it is 0 degree, but we are represented like this to know that this particular groups present here, but it is the angle is 0 degree. Okay, this is 0 degree, 0 degree, and that's why it is named as syn-periplanar. Okay, but if the heteroatom present there, like here, here also you can find that this particular carbon center OH gets the highest priority over this particular hydrogen. Similarly, in the back carbon, CH3 getting highest priority over these two carbons. So we have to check the relative position between these two particular groups. Here, these two are present at 60 degree torsion angle, so it is called synclinal. Similarly, this also here chlorine is there, and here in this particular group two chlorine is there, but you have to take one of the chlorine which is far apart for the naming. Okay, so this particular chlorine is 120 degree apart, so it is named as anticlinal, and we just omitting this particular chlorine because, and if we don't omit also, you can find if we take this particular chlorine, this particular chlorine and this particular chlorine is 120 degree apart. Okay, so we are naming this as anticlinal. Similarly, here also in this particular uh, center, carbon center, you can find that CH3 getting the highest priority, and in the back carbon there is two CH3 present. Now these two is CH3 present in the 60 degree torsion angle range and the plus part and the minus part itself. So it is called synclinal. Similarly, here also you can find that this particular carbon contain NO2 group as their highest priority group, and in the back carbon between NO2 and Cl, Cl getting the highest priority group. That's why this particular conformer name is syn-periplanar. Like for heterosystem, highest priority group will decide the naming. Okay, I hope this will be clear for you. Now we are move on to the conformational analysis of ethane. Now we know that ethane is the very simple molecule where this particular two carbon center is there, and this carbon center has contains three different hydrogen. Now this particular compound can present in only two types of conformers. So it shows two different type of conformers. One is the eclipse conformer and the staggered conformers. Okay, now since here in eclipse conformers, since this particular two hydrogen are very close to each other, so there is a torsion strain present, and due to this torsion strain, the energy of this particular conformer is higher than the staggered conformer. Like in staggered conformer, there is the torsion strain is lesser than eclipse conformer, and that's why it this particular staggered conformers are actually much stable than eclipse conformer. And then we are rotating this particular two bond, like here you can see this particular is the ethane molecule, or okay, so we have rotated this particular carbon carbon bond by 60-degree angle. So after getting 60-degree, okay, after we rotate the 60-degree here clockwise, so this particular hydrogen will again go for an eclipse conformer, and again the energy gap will be higher, and the energy gap is between these two conformer is 3 kilocalorie per mole. Okay, and this particular pattern is repeated throughout the 360-degree rotation of this particular bond, and after 360-degree rotation we got our same conformer back. So this is the simple ethane conformers energy profile diagram, where ethane can be present in the two different conformers. One is the eclipse conformer, one is the staggered conformer, and between this particular energy gap, there is a torsion strain difference. Like if it is rotated by 30 or 40 degrees, so you can check the particular energy from here. But these two conformer are the major conformer in the case of ethane structures, and the energy gap between eclipse and staggered is 3 kilocalorie per mole. Now we are moved to the n-propane. N-propane is slightly twisted compound, where this particular hydrogen can be replaced by a methyl group, and here we are shown the rotation between these two carbon center. Okay, so since this particular hydrogen now can be changed or replaced by methyl group, so here torsion strain as well as the van der Waals strain is present here, because CH3 is much bulky group than H, and due to this the eclipse conformer having the higher energy value over staggered. So it also contains two different conformers, eclipse or staggered. After rotating the particular molecule by 60-degree vicinity, we get the alternative eclipse and staggered conformers. Okay, so now we are moved to the very interesting compound, that is n-butane. Here, the potential energy diagram, or you can say the energy profile diagram, is little bit of confusing. So initially we began with the particular 0-degree rotation. In 0-degree rotation, that means it is an eclipse conformer, complete eclipse conformer. And in butane, we have to check the rotation between CH3, CH2, CH2, CH3. So here we are observing the rotation between this particular bond. Okay, so here two CH3 will be there, and in the eclipse conformer, when the rotation between this particular group is 0-degree, that means it has an eclipse conformer, and this particular two are the methyl group, and we all know that methyl group are bulky enough, and due to this a torsion strain also present here, as well as the van der Waals strain is also present here, and that's why this particular conformers have the highest energy. Now if we rotate this by 60-degree, so you get a new conformer, and this particular conformer is named as Gauge conformer, where these two particular bulky CH3 group are present 60-degree apart. Like this particular, the torsion angle between these two particular group is 60-degree in 60-degree plus rotation. Similarly, if we rotate anti-clockwise by 60 degree, we got this particular Gauss conformer. Okay, and these two Gauss conformer have a energy gap and the similar energy profile, because the both the torsion and as well as the van der Waals interaction or van der Waals strain is same here. Now here, since this particular Gauss conformer has been observed by clockwise rotation, that's why it is called a P Gauss. And this particular Gauss conformer has been observed due to the anti-clockwise rotation. That's why it is called a M Gauss. Okay. Now, if we again rotate this particular conformer by 60-degree rotation in any of the side, like clockwise rotation or anti-clockwise rotation, we have found this partially eclipsed conformer, where the particular eclipsing position, now there is not two methyl present is there, there is one methyl and one hydrogen present is there. Similarly, in the second part also there is a one methyl and one hydrogen present, but in the complete eclipse part, you can find that two methyls are present there. So it is simple that when the two methyl are present in a 0-degree angle, that means a complete eclipse, the torsion strain as well as the van der Waals strain is much higher compared to one methyl and one hydrogen present in a 0-degree rotation or torsion angle. Okay, so that's why this particular partially eclipsed structure have the lower energy barrier than complete eclipse conformer, but it has the higher energy potential energy than Gauss conformer. And after that, rotating by 60-degree more, we got the most stable conformer of n-butane, that is the anti-conformer. Here, this particular two CH3 group actually poles apart, that is a 180-degree angle, and that thus actually eliminating the van der Waals interaction. There is little torsion strain there. However, this particular conformer is the most stable in case of n-butane, and the least stable conformer is eclipse conformer, and medium conformer is the Gauss conformer and partially eclipse conformer. So this particular potential energy curve is very important. Like many times there is some question has been asked in the examination about the conformers of n-butane. So you must know this particular curve very well. Okay. So now we are moved to the some more complex system. But before that, we are talking about this particular thing, like why this particular staggered conformer or anti-conformer getting high stability over the Gauss conformer. Okay, so it is actually explained by the Gauss-butane interaction. The Gauss-butane interaction refers to the steric strain that occurs when the two methyl group, that is this particular two methyl group in butane, are 60-degree apart in staggered conformation. Okay, and due to this particular 60-degree torsion angle between two methyl group, this actually increase the potential energy compared to the anti-conformer by 0.9 kilocalorie per mole. Okay, and this term is called Gauss-butane interaction. And due to this Gauss-butane interaction, actually the Gauss conformer have the little bit of higher energy over anti-conformer. Now let us move to the some more complex structure, that is 2-methyl butane. So here you can find the 2-methyl butane is something like this, where 2-methyl group is present here. So here in the eclipse form, when the bond rotation is 0-degree, so here 2-methyl are present here in eclipse conformer, whereas this particular methyl will also getting eclipse with this particular hydrogen. So here extreme torsion and steric strain present. Similarly, here also torsion and steric strain present here. So this conformer have the highest energy over any of the conformers. Okay. Now, if we rotate this particular by 60-degree, so what happened that it is a little bit of Gauss form has been observed, but in terms of this particular methyl, it will be Gauss to this methyl, but for this methyl, these are anti. So it's not a peculiar structure has been observed. However, this particular conformer having the lowest energy because of the less static or van der Waals strain present here, and that's why this becomes the lowest energy over this particular other conformers. Okay, now after rotating the 60 degree, we got the partially eclipsed conformer, and partially eclipsed, there all the three centers or the three groups are actually partially eclipsed with one methyl and one hydrogen group, and that's why the energy profile diagram shows that the energy of this particular conformer is between 1 and 2. After rotating again 60 degree, we got the same type of structure in a different way. However, this also the same energy with as the two. So these two particular conformer, this conformer and this conformer is the most stable conformer of this particular 2-methyl butane structure. Okay. Now after rotating more 60 degree, we got our again this particular conformer, similar conformer but in a different orientation, where two particular methyl group are cis to each other and one methyl are actually having a torsion angle of 0 degree with one hydrogen of the adjacent carbon. Okay, so this also the same energy gap between this particular compound. Now here after rotating 60 degree again between this two this particular bond, then we got some interesting thing. Here you can see that all the CH3 are gotched to each other, like all the CH3 between all the CH3 uh, there is a torsion angle between 60 degree. Here in this particular case, the one CH3 have the torsion angle of 60 degree and one is the 180 degree. Here all the methyl group having the torsion angle of 60 degree, and that's why actually it has the higher energy compared to this 2 conformer and 4 conformer, and that's why it is present here. And after rotating 60 degree more, we got again same this particular conformer in a different orientation. That means this also have the similar energy of the 1 and 5 conformer. I hope it will be clear. So this type of conformational analysis you have to do in the examination if there is a trickier molecule has been given in the examination. Okay, so now let us do some conformational stability. Basically, this type of conformational stability has been observed in certain cases, and this is the exceptional cases, so you have to remember this particular thing. Like here, 1-bromopropane is more stable in its Gauge conformer over anti-conformer. Now, in our previous lecture, not in the previous lecture, in the previous discussion, we are observing that when the groups are anti to each other, they are more prone to more stability. But here in this particular compound, this particular Gauge conformer has more stable over anti-conformer. This is because that this particular bromine, that CBr bond length is much higher compared to C methyl or carbon-carbon bond. So what happened that this particular bromine, like all this particular bromine or methyl, this all having their own electron density. There is, or that we can say, their own van der Waals radii. So the van der Waals radii of the bromine is something like this, or we can say the electron density present like this here. Okay, and the methyl electron density is something like this. So what happened in this particular 1-bromopropane case, when this particular bromine and CH3 group are gotch to each other, so here you can find that there is a energy gap is there. Okay, so in the van der Waals cases, there is a two type of thing is there. One is the attractive force, one is the repulsive force. So when this particular two electron clouds are close to each other, then there is a repulsion, and when this particular two electron clouds are apart from each other, then this particular attraction observed. Okay, so what happened that in the case of Gauge conformer, these two particular electron cloud are as as apart each other, so they are actually attracting, and this attracting force actually stabilize the overall Gauge conformer over the anti-conformer, and that's why this particular 1-bromopropane is more stable in the Gauge conformer. Now it is written here also. The sum of the van der Waals radii between bromine and the carbon or present in the methyl is within the range of the van der Waals attractive force, and this stabilizes the Gauge form over the anti-conformer. Okay, so now if we check about another anomaly, this anomaly can be explained by the hydrogen bonding. In the case of ethylene glycol, it is observed that the Gauch conformer is more stable over the anti-conformer because of the hydrogen bonding. Like in anti-conformer, although this particular is stable, but there is a no additional hydrogen bonding possibilities is here. But here in this case, in the case of Gauch conformer, the hydrogen bonding is present, and due to this hydrogen bonding, this particular Gauch conformer getting extra stability over the anti-conformer, and that's why the Gauch conformer is stable. So whenever there is a chance of hydrogen bonding, you must consider that Gauch conformer might be stable over an anti-conformer. Okay. So now let us do some conformational analysis of 1,2-dihaloethane. So 1,2-dihaloethane, we can say something like this, where these two particular X group represent halogen, where the X is strictly bromine and chlorine, not fluorine. Like in this type of compound, when this type of 1,2-dihaloethane present and the halogen are bromine and chlorine, so here the main dominating factor is a dipole, and as well as the particular Fleck-Pole interaction or van der Waals interaction. Okay, so what happened that when this particular group are present in the anti-position, their particular dipoles are cancelled to each other, and this actually makes the particular anti-conformer stable over Gauch conformer, because here the particular dipole resulting, it contains some kind of resulting dipoles, but here the dipole is zero, as well as the since these two particular bulky group are poles apart, so what happened that particular groups are uh, eliminate the Fleck-Pole interaction, and that's why in the case of 1,2-dichloroethane and 1,2-dibromoethane, the more stable form is anti form rather than Gauch form because of this two particular reason. But when the X is fluorine, then Gauch form is more stable because of the fact that this particular in Gauch form, it presents due to the hyperconjugative interaction. So this particular group is present something like this, and due to forming like this, okay, this particular hydrogen and this particular fluorine are actually present in the hyperconjugative nature. So due to this particular present like this, so in fluorine case 1,2-difluoroethane, the Gauch conformer is much more stable over anti-conformer, because here this particular fluorine are actually cancelled, eliminating each other, but here it is present in the hyperconjugative structure, and that's why these Gauch are stable. Now there is a very interesting question that comes in every examination, especially if you are giving any kind of uh, college exams or university exam. Basically this type of question has asked repeatedly, where you have to determine the conformational stability between meso and active tartaric acid. First you have to know that how to change the mesotartaric acid Fischer form to Newman projection formula. As we know that already discussed in our previous lectures, like this particular is our front carbon and this particular is our back carbon. So we just simply make this particular Newman projection formula, and after that we have to rotate this particular form. And here you can find that these two particular CH3 are anti, as well as the OH are anti to each other, and there is a no chance of hydrogen bonding. So in case of mesotartaric acid, anti form is more stable than over any form. But in the case of active tartaric acid, you can find that when the methyl group is anti, okay, and this particular OH group are now have the closer vicinity to do hydrogen bonding, and the naming has strictly determined by the priority group. Here in this particular carbon, you know that the priority between CH3 and OH getting the highest priority over CH3 group. So here when the two OH are anti to each other, both the methyl are also anti to each other. But here when the Gauch form, when the two OH are Gauch to each other, the 2-methyl is anti, it is confirmed, as well as these two particular Gauch conformer have the closer vicinity to do hydrogen bonding, and that's why this particular Gauch form is more stable in case of active tartaric acid, whereas in the case of mesotartaric acid, anti form is much stable. So with this, we have to end this particular lecture. So it will be a vast lecture, and we are talking about so many different things. So it might be confusing for you. So if you find any kind of confusion, then I will request you to again watch this particular lecture, and I hope everything will be clear. So in our next lecture, we are talking about cyclic conformers. Okay. So thank you for this for your time, and thank you.